Can you see the slides?
Yes.
Okay, cool.
Okay, so today I will be the chair of this the session. So we'll start the day with two presentations by Feliciano, and then we'll have a short 10-minute break, after which we are going to resume with a hands-on lecture by Hyun-Jung Lee. And then we are going to have the first tutorial that will be dedicated entirely to the EPW code. I think the presentations are going to be made available online. Have already been made online available, the ones from yesterday?
Yeah. If you go to the website, you can see all the one from yesterday, including the first hands-on. Yeah.
Okay. So I think with all this, I will give the floor to Feliciano for his first lecture today.
Okay, thank you, Roxana. So you can hear me, right?
Yes, we can hear you perfectly.
So good day, everybody. So today, what we're going to do to start is to discuss a little bit the theory of electron-phonon interactions. And this discussion is structured into two lectures. So the first one, this one, will be based on elementary concepts. And I assume that many of you are already familiar with most of these concepts. So please bear with us. The second part, the second, let's say, 45 minutes, will be about more advanced concepts. And that's about many-body methods for electron-phonon interactions. So that will be a little bit more advanced, and we will go through some of the key equations that are needed to understand what is going to happen throughout the rest of the school. Okay. So let me get started. And so today, what we want to discuss now is how to think about electron-phonon interactions from a very simple point of view. So that's what I call a heuristic approach to the problem. Then I will give you a few examples of electron-phonon interactions as observed in experiments. Then I will move to trying to describe electron-phonon physics using elementary perturbation theory. So that is what is called Rayleigh-Schrödinger perturbation theory. And then in the last part, we will go over some details about the electron-phonon matrix elements and the concept of one interpolation that you saw yesterday, but applied to electron-phonon matrix elements. Okay. First question is, where do we see electron-phonon interactions? So where do they arise in the calculations that we perform? So since yesterday, you saw the presentation by Paolo Giannozzi on density functional theory and the quantum espresso project. Let's pick up from there. So this is very simply the Kohn-Sham equations for electron wave functions. V sub SCF is a self-consistent potential, and the idea is that we try to solve these equations in standard electronic structure codes to obtain the energies and the wave functions. So once these wave functions are calculated, we can obtain the electron density by adding up the square moduli of the wave functions for the occupied states. And now the key features of density functional theory is that it provides us with a recipe to construct the self-consistent potential starting from this density. For example, here is the Hartree potential, and here is the exchange and correlation potential experienced by the electrons. The self-consistent potential also contains the Coulomb potential exerted by the ions on the electrons. Here is written as a bare Coulomb potential. In most codes, in practice, this has to be evaluated via pseudo-potentials. So once this is constructed, we bring it back, and then we solve this set of equations self-consistently. So we all know about this, so there is no need to say much more. But the key piece of information I would like to convey here is that the ions, so the atomic positions, appear only in this red bit here. So tau sub k is the position of the atom k in, let's say, in the unit cell. All right. So if we look for electron-phonon interactions, we must look into what happens to this variable. Now, the self-consistent potential depends on these positions. So when I plug the self-consistent potential in this equation, what that means is that the solutions, so the wave function, the energies, will also depend on these positions, okay? So everything that we do is a parametric function of the atomic coordinates. So let's now write the potential as a position depending on the position of the electrons and the atomic positions. And let's consider a situation where you have a crystal at equilibrium, for example, with the positions of the atoms determined by X-ray crystallography. And let's imagine making a very small displacement of an atom from equilibrium. If that is the case, we can perform maybe a Taylor expansion of this potential with respect to the displacement. And in the case of a single atom moving and a single Cartesian direction, we have an elementary expansion like potential at equilibrium plus linear variation, quadratic variation, and so on. So in practice, the first term, so let's say the zeroth order term, is the potential at equilibrium that we usually calculate in DFT calculations after we optimize the atomic structure, okay? Whatever follows is what we can consider the perturbation Hamiltonian that leads to electron-phonon interactions, okay? So electron-phonon interactions correspond to having these displacements, u squared, and so on, different from zero. So the goal of this first lecture is to understand what we can learn by examining this perturbation Hamiltonian and how we can deal with that. So before getting there, let me give you 4 examples of what happens as a result of electron-phonon interactions. So these figures are from the group of Andraschkish in Lausanne. These are from the very first measurement of mobilities in molybdenum disulfide when they made the first field effect transistor based on a monolayer molybdenum disulfide. And this quantity, the mobility, will be discussed in detail tomorrow, but just to anticipate, it is a measure of how fast electrons move in a semiconductor when you apply an electric field. The important point here is that this measured mobility depends on temperature quite strongly. So you can see it changes by 2 orders of magnitude from low temperature to room temperature. And this is an effect of electron-phonon interactions. So the second example is about solar cells. So you know that most solar cells are based, so look like this more or less. So this is silicon cells. This is most of the cells mounted on rooftops. And what is interesting about silicon solar cells is that the silicon crystal is an indirect gap semiconductor. In particular, that means that the first allowed optical transition happens approximately around here at 3 electron volts. So the black line is the measured absorption coefficient as a function of photon energy. And if there were no phonons, silicon would not absorb any light in this range, but this is precisely the range where sunlight is the strongest. So you have the visible here and the infrared. So most of sunlight is concentrated in this range. And the reason why silicon absorbs here is because there are things called phonon-assisted optical transitions that are again a manifestation of electron-phonon interactions. Maybe one of the most spectacular manifestations of electron-phonon interactions is the phenomenon of superconductivity. So these data are from the group of Eremets. They discovered in 2015 that if you compress sulfur hydrides at extremely high pressures using a diamond anvil, you have transitions to superconducting phases at extremely high temperatures, of the order of above 100 Kelvin. So this means that when you look at the resistivity as a function of temperature, by lowering the temperature, the resistivity goes down as in every metal, but then at some point it suddenly jumps and it goes to 0. And that is the marker of a transition to a superconducting phase. So how do we know that this is related to phonons? Well, the single most important experiment to prove that is the isotopic substitution. In this case, for example, if you start with a material composed of sulfur and hydrogen, and you replace hydrogen by deuterium, which is twice heavier, what happens is that the vibrational frequency, so the phonon frequency, decreases, and correspondingly, the critical temperature also decreases. So that's typically considered a smoking gun for a phonon-mediated superconducting transition. Okay. And finally, the last example I want to give is how the band structures of semiconductors depend on temperature. So on the left, you see an example, like a schematic of something called metal ammonium lead triiodide. It is a perovskite structure with lead in the middle of the octahedra, iodine in the corners, and this little molecule, metal ammonium, the metal ammonium cation in the middle of the cages. So this is one of the famous perovskites that now is considered for, is being studied for solar photovoltaics. And this is a measurement of a related system. It's very similar, but it contains formamidinium instead of this molecule here. And it is a photoluminescence measurement. What that means is that the band gap of this material is of the order of, let's say, 1.5 electron volts, let's say. So this material is excited about the band gap, for example, with a green laser at 2 electron volts. The photoexcite carriers relapse towards the band extrema. When they reach the band edges, they recombine, okay, by emitting a photon. So these lines here at a given temperature are the peak of the photon emission at each temperature. So you can see that this peak goes from maybe 1.47 electron volts to maybe 1.57 electron volts at high temperature. So there is a dependence of this band gap on the temperature. So this is also, again, an effect of electron-phonon interactions. So what I want to do in the next few slides is to try to show how we can capture some of these effects using very simple arguments. So first of all, let me go back to our potential at equilibrium. This is a very simple cartoon where the dots represent the atoms and the black line is the self-consistent potential, let's say from a DFT calculation. Now let's imagine moving one of the atoms a little bit. So what is going to happen is that the potential is going to be deformed. So we have I'm going to have a deformed potential, and we can describe this new situation as the sum of the equilibrium situation plus their difference, okay? So this would be the potential perturbation that we need to investigate. And it is shown here as something looking like a dipole because all these atomic displacements generate things that look like dipoles, okay? In the general case, when you have many atoms moving, there will be a sum of such dipoles. So what we want to do now is to understand how a description of these perturbations can be used to calculate some physical quantities. And what I want to do is to convince you that one does not need to look very far to do this. And in fact, what you can do is to open your favorite quantum mechanics textbook, go to the chapter on perturbation theory, and look at the 3 most important recipes for elementary perturbation theory. It is also called Rayleigh-Schrödinger perturbation theory. So the first one is the change of the energy, so the eigenvalues of electrons as a result of a perturbation. If this is the perturbation that results from the displacement of an atom, okay, the change in the energy eigenvalue is obtained by taking the expectational value of this object over the unperturbed electronic state, for example, the Kohn-Sham state. The second most important recipe is the change of the wave functions to first order. So that is given again by something that involves this potential. This time we have off-diagonal matrix element and the energy denominators here. And then there is the wave functions of the unperturbed system on the right. Okay, so these are the change of energy and wave functions in first order time independent perturbation theory. So this would apply if the displacement of the atom is static. So we displace the atom and that's it. So there is another possibility, and that's where, for example, the atoms are fluctuating. So, for example, this displacement is a cosine function of time, maybe because we are driving the system using a laser. So in that case, we need to use the time-dependent Schrödinger's equation, and therefore the time-dependent perturbation theory. And the key formula there is the transition rate from an initial electronic state to a final electronic state as a result of this perturbation. So this is given by the square moduli of the matrix elements again, times some Dirac delta functions that ensure energy conservation. So this is obviously the famous Fermi golden rule, okay? These 3 recipes are kind of almost trivial for this audience, obviously, but I would like to emphasize that they are very important because the first one is the key to understand temperature-dependent bond structures. The second one is the key to understand phonon-assisted optical processes, but also the formation of polarons. And then the last one is important to understand phonon-limited transport coefficients, for example, like the mobility I mentioned before. So what we're going to do in the following is to give examples of each of these 3. But before getting there, let me comment a little bit on this displacement here, okay? If you look at this expression, you realize that the change in energy will be proportional to this displacement. So if I choose a large displacement, I can get a very large change in energy, for example, in the band structures, and similar in the other quantities here. So it is important not to make an arbitrary choice for the atomic displacement. So how do we decide that? there are essentially two scenarios of interest. So the first one is when your system is at equilibrium. That means that you are studying an experiment that is being conducted at constant temperature. So that's the most typical case. So you have an equilibrium situation. The second case is when you have out of equilibrium. For example, I'm sure you are aware that now there are many experiments being carried out where people drive specific phonons by coupling them to light. And in this case, you will not have an equilibrium population of phonons, but you will have a specific phonons with very large amplitudes and following specific time patterns, okay? So that's something that is a little bit more complicated to describe. And that's why in this school, we will focus on equilibrium properties, okay? So how do we describe the displacement at equilibrium? The answer is actually quite simple if you are looking for harmonic systems. So harmonic approximation means that we truncate the expansion of the potential energy surface of the atoms to second order. And by performing a unitary transformation, we can always rewrite all the atomic displacements as a set of independent quantum harmonic oscillators. So in practice, one can map the system into a number of harmonic oscillators that are physically equivalent to a simple spring, where you have a mass attached to the spring, you have a spring constant, you have a displacement that indicates the position of the mass, okay? So the question now is, what is the average displacement at a given temperature? Well, if you consider the spring, you can clearly guess that the average displacement per se will be 0, because the number of times the sphere finds itself on the right of the equilibrium position will be equal to the number of times it finds itself on the left. So the first term that is going to be non-zero must be the quadratic displacement. Now, for the quadratic displacement, there is a very elementary way to derive it, and that's using the equipartition theorem. So you can say that the kinetic energy of the oscillators is equal kBt half for each degree of freedom, and by inverting this relation, you obtain that the mean square displacement at a given temperature is very simply proportional to temperature, okay? So that means that when you increase temperature, the square displacement in a crystal, for example, will increase linearly. Now, is this enough for our calculations? Usually it is not, because we want to describe quantum effects. So one has to replace this expression by its quantum counterpart that is obtained very simply by taking the canonical average of this square displacement using the eigenstates of the quantum harmonic oscillator. So that gives very simply the Bose-Einstein distribution that depends on the phonon frequency and the temperature. So the blue, let's say the quantum statistics, gives this blue line here, and you can see that at high temperature, quantum and classical distributions are very similar, and at low temperature they deviate because in the classical case, atoms stop moving completely at low temperature, while in the quantum case, you still have some residual motion that is what we call the 0-point motion, okay? So this picture is very simple, obviously, but it is very useful to keep in mind when it is useful to use, for example, molecular dynamics to study temperature effects, and when that is not appropriate. For example, if your system is being considered in this regime, maybe you can use molecular dynamics very simply, but if you are in this regime, obviously that will not cut it. So the important thing to remember is that the divide between, let's say, the quantum regime and the classical regime is the half of the characteristic phonon energy. For example, if you are considering a perovskite with lead, typical phonon energies are of the order of maybe 10 millielectromoles. That means that this value here will be approximately 5 millielectromoles, and that's 1/5 of room temperature. So we are saying that this is approximately 60 Kelvin in perovskites. So room temperature will be approximately here. So maybe your system can be described using classical molecular dynamics. If you're considering, on the other hand, something like graphene, typical phonon frequency energy is of the order of 200 millielectromoles. So this is going to be 100 millielectromoles. So room temperature is approximately here. So in the case of graphene, using classical dynamics is not going to cut it, okay? So that's a very simple way to distinguish, to keep in mind when you need to use certain approximations. So now let's see what we can do with these displacements when we apply the three formulas that I gave you a second ago. So first of all, let's look at band structures. I say that the change of energy with respect to the, as a result of electron-Phonon interaction can be written using this simple formula. However, there was a little bit of a cheat because I didn't tell you at the time that the average displacement vanishes at equilibrium. So this, in the case of equilibrium calculations, has to be 0. So the first term to consider is the one containing the square of the displacement, and that can be simply done by taking the same perturbation, but to second order in perturbation theory. Okay, so that's very simple, and it's something proportional to the square displacement that will be non-zero. Now, since there is a term proportional to u square, one can also take the second derivative of the potential, so basically the second variation of the potential times u square to first order in perturbation theory, and that gives you another term looking like this. In practice, what people do is to try and put together these terms. You will have the change of energy given by some matrix elements here, summed over the various states, and then times the square displacement. And to find the temperature dependence, you take the canonical average of the entire equation. So here you will have temperature as a function of time, and here you will have the Bose-Einstein population. So that's the essence of the Allen-Heine theory, and there is much more work that has been done to generalize it to cases where one includes phonon frequency denominators and so on. So there is much work by the group of Xavier Gonz on this. I will not go into details because this will also be discussed during the school. Let me just explain what one could expect from these expressions. So if you look here and you just focus on this part just for simplicity, you realize that there is something positive and then energy denominators. So let's just focus on this term. And let's imagine a semiconductor with a conduction band and a valence band here. So if I want to look at the change of energy of the conduction band bottom, I need to place the eigenvalue of the conduction band here. And these other things are energies correspond to summations over all possible states. Now, the summations that contribute, the terms that contribute the most to the sum are those that make this denominator very close to 0. So these are really summations over states that are very, very near the band bottom. For states near the band bottom, this energy must be above the conduction band. The conduction band is the minimum by definition. This means that this denominator will be negative, okay? So this term overall is a negative term. Similarly, one can do a reasoning for the valence band and discover that this term will have to be positive. This means as you switch on electron-Phonon interactions, typically the conduction band will go down and the valence band will go up. And therefore, when you try to look at the band gap will tend to decrease with temperature, okay? So the decrease is this red line, and this is the typical behavior that you will find for standard semiconductors. I should emphasize that this trend is not universal. There are many semiconductors for which this is not the case. There are interesting cases to study. For example, the perovskite I mentioned in the beginning as an example. But this is a way to understand, at least at a basic level, what is going on. Just as a matter of completeness, let me emphasize that this red line corresponds to considering the quantum harmonic oscillator for the displacements. So if you were to perform molecular dynamics and your system was harmonic, and if you track the band gap, you will find this blue line, okay? So there is a little bit of a difference. And that means that let's say, molecular dynamics calculations will not give you exactly the same as a complete perturbation theory calculation of the band gap. In particular, if you do the calculation at 0 temperature in the FT, you will not hit the, let's say, the real band gap of the system at 0 temperature, because you are looking at this kind of value here, while what is being measured by the experiments is this value here. So the difference is what is called the 0-point renormalization of the band gap, okay? So let me give you an example of this. The calculation was performed by Marius Zacharias, and this I think will be shown in the tutorial on Friday. So what you see here is the band structure of silicon, has been already discussed yesterday. So this is valence band, conduction band. The red line, the black line is the band structure using standard DFT at 0 Kelvin, so the atoms at equilibrium. As soon as you switch on electron-Phonon interactions, the black line turns into the blue line. So that's 0 Kelvin, but including quantum 0-point effects. And then if you keep dialing up the temperature, you obtain the red line. So the band keeps shifting a little bit up with temperature. And the opposite trend is found for the conduction. So if you take the difference between conduction and valence band edges, you find the band gap. And these are the calculated values, the blue dots. Okay, so you can see that band gap goes down with temperature, and in comparison, the experimental data are these triangles, and you can see that the agreement is reasonable. The disagreement here at high temperature has to do with the fact that the electron-phonon interaction calculated at the DFT level is slightly too weak because of the DFT band gap problem. Okay, so that is something that we can discuss separately if you like. Now, let me tell you a little bit about optical absorption. So we are moving to the second recipe of perturbation theory. In the case of the change in the wave functions, I say that the wave function change using this, let's say, recipe, which involves some matrix element, energy denominators, and wave functions in the unperturbed system. So what this has to do with optical absorption? So let us remind ourselves how to calculate an optical absorption spectrum in the simplest possible way. So this is an expression for the independent particle approximation, and it's very simply the imaginary part of the electric function that is proportional to the absorption coefficient, and is given by a joint density state. So these are conduction band states, valence band states, photon energy, and this joint density state is weighted by some matrix elements. So these are electron-photon matrix elements. In this case, this is written in the electric dipole approximation. Okay, this is the simplest possible thing you can do. Now, in this expression, the conduction and valence band Comsham states are calculated using the equilibrium atomic positions. So what happens if I include electron-phonon interactions? So what I can do is to consider that each wave function will be modified by this expression. So if I take this expression and I modify the valence wave function here, I will have valence plus delta valence, where the delta is this object here. And then if I replace this expression in the conduction, I will have conduction plus delta conduction. So if I perform now the matrix elements, I will have 4 terms. So conduction times valence, conduction times delta valence, delta conduction times valence, and delta conduction delta valence. So I will not write all the 4 terms, but I can give you one just to show you what is going on. In these terms, if we combine this matrix element and this object, you discover that there will be a product of 2 matrix elements, electron-photon, electron-phonon. So you have a valence state going to an intermediate state. Then from the intermediate state, you go to a conduction state. The first transition happens through a photon and the second one through a phonon. So what this should remind you is that the usual picture that you see in any textbook on solid state physics or semiconductor physics, where you have a band structure and an indirect gap. So you cannot make this transition without phonons, but you can go across the indirect gap by first making a direct transition, which is vertical in momentum space by a photon. So that's the first matrix element. And then a transition that does not concern momentum for the electrons into the conduction band bottom via the second matrix element. Okay, so that's basically a statement of the fact that the momentum selection rule that exists because of the block translational periodicity of crystal is broken when you have electron-phonon interactions, because the phonons correspond to a dynamic distortion of the lattice that induces asymmetry breaking and therefore makes it possible to make these transitions. Okay, so let me just give you an example. This is something that we will see on Friday by Mario Zacharias, and there are very similar data that will be discussed using perturbation theory by Manos Koupakis on Thursday. So this is the optical absorption coefficient measured for silicon. You see this is the photon energy. This is the fundamental gap of silicon of 1 electron volts, the direct gap of 3 electron volts. So this is the fundamental gap, and this is the direct gap. So if you perform DFT calculations, okay, you find without phonons, you find this absorption. Okay, so it goes slightly below the direct gap just because of some broadening. Notice these are logarithmic scale, but this means that the only transitions that are being picked up by these calculations are direct transitions. Okay, so we don't see the indirect gap. As soon as you switch on the electron-phonon interactions, you recover the missing transition here, and that means that we can make transitions across the gap, and that is essentially the mechanism of breaking symmetry that I just described in the previous slide. Okay, so notice that in these calculations, the agreement with the experiment goes over several orders of magnitude. So you will see much more of this on Thursday and on Friday. And the last example I want to give you is about carrier relaxation times. So the recipe of time-dependent perturbation theory, the Fermi-Golden rule, is very useful to study transport. So I gave you an expression to determine the transition rate from an initial state to a final state. So if we want to know how long an electron stays in a given state, we can just adapt all the transition rates from an initial state to all possible final states. So that would be the time that the electron stays in a given state. So that's what we call the relaxation time. If you want to study transport, you can find out, starting from the Boltzmann transport equation that will be described tomorrow by Samuel Ponce, that under very simplified assumptions, so this is not for practical calculation, but just to understand the concept, one can write the mobility using a very, very simple expression. This involves something called the relaxation time approximation. And this expression is simply the product of the electron charge divided by the electron mass. Then there is a summation of all these relaxation times weighted by some dimensionless weights, okay, that have to do with the population of the carriers and some scaled kinetic energies, okay? So the only bit I want you to keep in mind is that this is a summation over, is a weighted sum of relaxation times, and therefore it is also a relaxation time. If you call it average relaxation time, you recover what is called the Drude formula that you find in any textbook like Ashcroft and Mermin, okay? So this is to say that the perturbation theory already gives you the key tools to understand some of these more complex phenomena. The theory of transport will be done more in detail tomorrow by Samuel Ponce, also discussing many body effects, okay? So this is just a way to give you a very quick idea of what happens. So this is a calculation, again, by Samuel, where the experiment, so this is for the perovskite I showed you at the beginning. The dots are terahertz photoconductivity measurements by the group of Mike Johnston in Oxford. And these are done on single crystals, like these large single crystals. And these are calculations using the Boltzmann transport equation. And you can see that the predictive power of these calculations is really improving. And we are getting to the point where you know, one can really interpret and help experimentalists, you know, move forward in the study of transport in even very complicated systems. So now, in the last maybe 5 minutes, what I would like to do is to give you some detail on the electron-phonon matrix element that I've been discussing here. Okay, so I've been calling this the matrix element without using any wave vector indices, just taking the derivative with respect to one atomic direction and atomic position. And that's only to understand what happens. In practice, the situation is a little bit more complicated. And what we must use in calculations is an expression that contains many more indices. So this object gets transformed in real calculation in this quantity. So let's go through the details. So this quantity has two wave functions that are the block periodic part of your, let's say, Kohn-Sham wave functions. So these were introduced yesterday by Nicola Marzari already. So there is not much to say here, apart from that n is the band index, k is the wave vector. And then I would like to tell you a little bit more about this delta V in the middle. So this is the variation of the self-consistent potential for a given phonon, wave vector q, and mode nu, okay? So this is the explicit expression. And let's go through the expression to understand what is in mode. First of all, there is a display, the variation of the self-consistent potential with respect to the displacement of a single atom along a given direction, okay? So this is this dipole that I showed in a cartoon a few slides ago. Once you have this change for every atom, you need to decide in which directions the atoms are moving. So that direction is given by the phonon polarization, which are the eigenmodes of the dynamical matrix introduced by Tyler Jones yesterday. So you know the change, you know in which direction the change takes place. You need to know now how far the atoms are moving, and that's given by the 0-point amplitude for each vibrational mode. Finally, we need to consider an incommensurate modulation that will give this displacements, this potential, the same periodicity as the phonon that we are considering, okay? So this is a little bit complex, but is what is being calculated in the in codes like phonon code and the EPW code, okay? So notice that here we transform a set of atomic dipoles into a periodic potential. That's something to keep in mind for the next couple of minutes. So what is the challenge with these matrix elements? Here I'm giving you an expression that is an extremely simplified version of the lifetime of an electron in a metal, okay? So this is written starting from the full expression, making the adiabatic approximation and the high temperature approximation. It is not something that we typically use for calculations because we can do much better, but it's simple because we can take a look at the terms without spending too much time. So this is just to say that the rate of basically the scattering rate, or if you want the image lifetime, is proportional to temperature, but most importantly, it depends on an integral that involves all possible phonons, the electron-phonon matrix elements, and these delta functions that tell me that if I want the lifetime of the electron nk, I need to consider all possible scattering into the other electrons that have the same energy. For example, if my electron is initially on the Fermi surface, I need to consider all possible scattering events that start from the Fermi surface and end up on the Fermi surface. So here you can probably see the challenge of the problem of this calculation, because if in a self-consistent calculation, we typically need maybe 5 by 5 or 10 by 10 by 10 grids in Brillouin zone, here we will need much more because we need to describe carefully the entire Brillouin zone, okay? So typically these calculations require something of the order of 100 by 100 by 100 points, like millions of points. So that's very expensive. But most importantly, each matrix element requires the calculation for a phonon with a given Q vector. So that is as expensive as a DFT calculation, okay? So that's why this is expensive. So performing calculations of this type and many other properties that have to do with electron-phonon interactions require the evaluation of this matrix element on very dense grids and in an efficient way. And that's why there are many techniques around to try to do this efficiently. And we settled on the use of one-E functions. And that's why yesterday you had a lecture by Nicola Marzari and the tutorials by Giovanni Pizzi and Jun-Wen Chao on the one-E functions. So the idea here, I will not repeat what you learned yesterday, but just to recap, the one-E functions are an alternative representation of the electronic states, like quantum states, that is localized in real space. So instead of having periodic functions like the block functions, we like this one, we do a unitary rotation that leads to some localized functions. And 1E90 is what is the engine that is used to determine the best possible unitary matrices that allow you to find localized functions. So why this is useful? Well, let's imagine that we can rewrite the electron-phonon matrix element using 1E functions, okay? So instead of a block wave, I'm going to do a rotation and obtain a 1E function. The other block wave is also represented by a 1E function. And then instead of the periodic part of the self-consistent potential, I'm going to use the dipole of each atom. So this means that we might have 3 localized objects in the matrix elements. And that implies that if these 3 objects are sitting far away from each other, maybe the matrix element will go to 0 quickly, and I don't need to calculate too many matrix elements, okay? So what is the key to this operation is to establish a unitary rotation between the matrix element in the standard block representation and matrix elements in the 1E representations, okay? So this formula is very similar to the one that you've seen yesterday for wave functions. It just contains double integrals because we are both transforming electrons and phonons, okay? So this is always exact, but the key of the interpolation is that if this matrix element decays very fast as a function of the distance between these 1E functions, maybe I don't need too many matrix elements in order to generate my block matrix element on a very dense grid, okay? So that's the core concept of 1E interpolation of the electron-phonon matrix element. So what one has to check is how localized these objects. And here I want to give you an example for diamond, which is very old, from what, 15 years ago or more. So this is the electron-phonon matrix element that is calculated in the following way. So we keep one 1E function and the dipole coming from the atomic displacement in the original, let's say, central unit cell, and we move the second 1E functions further away. So this is the matrix element as a function of this distance. You can see it decays quite quickly, and it's basically an exponential decay here. The second plot is a slightly different experiment where you take the 2 1E functions, you keep them in the same unit cell, and then you move the atomic dipole further away. And again, you see that in this case, it decays very quickly, okay? So because of this quick decay, what happens is that you can perform calculation the matrix element on coarse grids, for example, uniform grids like these ones, then go to Wannier basis and then interpolate back on any point of the Brillouin zone. So this is, for example, a calculation where the blue dot, so the black dots are direct, quantum espresso calculations on specific incommensurate wave vectors in Brillouin zone, and the red line is what is obtained by Wannier interpolation starting from uniform grids. Okay, so that means that with a calculation over just a small grid of points, you can generate millions of points without too much effort. Now, the question is, at this point, the Wannier functions, as you saw yesterday, Nicola Marzari explained that for insulators, one can prove that Wannier functions can be made exponentially localized. So that's very good. In the case of metals, the situation is more tricky, but we still hope that they will be sufficiently localized. Now the question is, in the case of the displacement, the potential of the nuclei, so how do you know whether that is going to be localized or not? So I think we can do the following reasoning to figure that out. If you move an atom, that will generate essentially a potential variation. And for this potential variation, you can always perform a multipolar expansion. That's an exact expansion that can always apply to any kind of charge distribution. So you will have the dipolar term, the quadrupolar term, octupolar term, a sextuple, and so on. Okay. So the dipole is the usual thing where you have a plus and minus charges. The quadruple is plus, plus, minus, minus, and so on. So this is basically the bare perturbation of the nucleus. But the self-consistent potential is the bare perturbation screened by the dielectric matrix of your crystal. Okay. So the way to understand this expression that I've written very, very quickly is the integral of epsilon minus 1 of r prime times the bare potential in r prime. So it is truly a convolution. All right. So to understand how this behaves in momentum space, we can perform Fourier transforms of this bit, Fourier transform of this bit, and multiply. So what are the Fourier transforms? For the dipole, you discover that the Fourier transform of 1 over r squared is 1 over q. Okay. So q is the phonon wave vector. So this goes to infinity when q goes to 0. So when you have long wavelength phonons. For the quadruple, this is of the order of 1. It does not diverge, but it is discontinuous, so it is direction dependent. And for the octuple, it is linear in q, then it will be q squared and so on. So these are basically the Fourier transforms in reciprocal space of these bare potentials. What happens to the dielectric function? So that will depend on the system we study. So let me give you two examples, one for the electron gas and one for the simplest model of a semiconductor. So the dielectric function can be written in the following way. For a metal, we have the Thomas Fermi dielectric function. So what we discover is that the dielectric function as a function of wave vector goes as 1 over q squared for small wave vector. So if q goes to 0, this quantity will go to infinity. Now this is interesting because if you take epsilon minus 1 and you multiply by this guy, the infinity here cancels the infinity here. Because of that, this dipolar interaction in the case of metals will be regular. And the same goes for the quadruple and the octuple. If you now look at the dielectric function for the insulator, if I take q going to 0, so this term will vanish, and this dielectric function will be just epsilon naught. So this is the high frequency permittivity. So this tends to a constant, and therefore it will not be able to screen this object. So bottom line, if you try to look at the self-consistent potential in momentum space, you will find that in metals, these will be mostly smooth as a function of wave vector. But in insulators, near q equals 0, so at long wavelength, so the dipolar term will be singular, the quadrupolar term will be discontinuous, and then you have something that becomes smoother. Okay? So this means that one has to be very careful in performing this interpolation because you are dealing with something that may not be localized. What is the practical implication? So this will be discussed in detail tomorrow, but I just want to give you an example. This is the matrix element for a longitudinal optical phonons in titanium. The dots are standard DFPT calculation. You can see that when you go to gamma, so q equals 0, this goes to infinity. Okay. If you try to attempt a Wannier Fourier interpolation, like I gave you, the formula I gave you earlier, you will see that away from the q equals 0, the interpolation works fine. But near q equals 0, you have a problem. You cannot capture this singularity because this kind of physics is simply not included. So the strategy that's been developed by us and other groups in the past few years is to treat these singularities in an analytical way Okay, and when you do that, you recover the correct matrix element as you would expect. So I will not give the formulas, but just to mention, this is similar to what Paolo Giannotti mentioned yesterday about the LOTO splitting in polar crystals, when you need to add an extra non-analytic term into the dynamical matrix. In this case, this term has to be, a similar term has to be added to the electron-phonon matrix element. So that's basically the end of this first part, and the take-home messages are that we can really understand at least the key concept of electron-phonon physics, starting from the three basic formulas of elementary perturbation theory. The challenge starts when you want to evaluate integrals in the Brillouin zone, because matrix elements are expensive quantities, so one has to find efficient ways to compute them. And the third message was that the matrix elements in metals and insulators behave very differently, and this has to do with the difference in the screening in metals and insulators at long wavelength. So we need to be very careful when applying interpolation techniques, and we have things like polar insulators. Okay, so this is the last bit, and this is a set of references that you can take a look at. You will see this on the schedule with in the PDF, so you don't need to write them down. You have all the links here. I just want to mention some latest developments. What I mentioned about the dipoles has been discussed in these papers here. And I didn't have time to go over quadruples, but there's been some very nice work recently by two groups. So you will find this work here, and this is activity that is still continuing to this day, and it's been embedded in most of the codes doing electron-phonon interactions. Okay, so this is the end of the lecture, and I'm happy to take questions if I didn't go too much over time.
I think we have 3 minutes for questions before we can move to the next talk. Your next talk. So they are in the Q&A. In fact, there are 7 right now. So
so I need to, okay, Q&A.
Would you like me to read them?
I can go there. So, okay. Is it possible to obtain second order electron-phonon interaction from EPW? Third term on slide 14. So let me just go slide 14. So this is something that cannot be obtained because it would require basically higher order perturbation theory in the phonon code. However, there is a way to calculate this term now that has been implemented in Quantum Espresso recently, so that should not be a problem anymore. Okay, not the specific term, but the summation of these terms. Okay, so for the mobility calculation you show for mapping, my understanding is that polarons play an important role in transport, but these calculations agree quite well. Would the agreement improve if polarons effect were considered? So for MAPI, let me just go here. Yes, that's actually a part of an ongoing discussion. So we will have a lecture on polarons on Thursday. Actually, I will give you a slide about the strength of the electron-phonon coupling in MAPI in the second lecture. Okay, and basically what we know is that the polaronic mass enhancement in MAPI is the order of maybe 20 to 30%. So it's not gigantic. It's similar to other semiconductors. So when people refer to polaronic effects, they are mostly referring to rotations of the cations. Okay, so that's a little bit trickier because it involves anharmonic effects. Okay, but those effects should not be important in this temperature range. Okay, I hope that that's answers the question. So now, does the JDOS also change in phone-assisted optical absorption in addition to the wave function change? Slide 17. Yeah, actually, that's a very good point. So what I guess the question is, I'm changing the wave function, but I could also change the energies. Actually, this is precisely what was done in a work by Manos Koupakis in 2012. So that was the first calculation of optical absorption using perturbation theory. They changed both the matrix element and the energies. So I'm positive that we will discuss this aspect on Thursday. Okay, so the next question is why there is an incommensurate term is right 21. Okay, so I guess we're talking about this term. So this actually is because we are enforcing a displacement that does not happen, is not periodic, but has a periodicity, so has a wavelength that is essentially 2 pi over q, okay? So to have a phonon that spans more than a unit cell, if you do the maths, you discover that you have this a little bit popping up, okay? So next question, slide 25. So the meaning of the y-axis in the left decay picture. The meaning of the y-axis. So the so let's look at this picture. So this is the matrix element in the one-year representation. The first coordinate represent the. So let's say that one electron wave function is in the 0th unit cell. The second one is sitting in the unit cell denoted by the lattice vector R, and 0 means that the atomic dipole is sitting also in the origin unit cell. So capital R gives the distance, let's say, between one of the one functions and the dipole and the first one function. Okay, and we can say that this is localized when you discover that your matrix element become orders of magnitude smaller when you move a few unit cells away. Okay, ultimately, one, as Nicola Marzari said yesterday, one should always converge calculations with respect to this truncation in practice.
Feliciano, I would suggest maybe one more question, and the other maybe you will answer in writing after the second talk, if we don't want to.
So let me read the second. So the first one, method did capture the infinite equivalent 0. Wasn't the idea to avoid them? I mean, no, there was no idea to avoid the infinity. So the point is that so this behavior is something physical. So this kind of divergence, so we cannot just remove it. So the one-year Fourier interpolation method is very simply a way to not compute these dots one by one, because that would be very expensive, but being able to compute them very efficiently using an interpolation method. Okay, so this is exactly the same as what happens for dynamical matrices in polar semiconductors, for example. Okay, so I'll stop here, Roxana, so that we can go.
Yes, I think so. If we don't want to be too much behind, and for some questions, probably we answer in writing. If not, once you're.
I can also answer, later after the second bit.
Sure, sounds good.
So should we start the second one, or I want to?
Yes.
2 minutes?
Yes.
Okay. Yeah. All right. Let me just.
Sorry that there won't be the 5-minute break in between.
Yeah. Let me just unshare this because I need to change